I don't have to go back and re-record from before. So a couple quick reminders. You've got your homework that is due on Sunday. You've got your extra credit that is due on Saturday, 11:59 p.m. You've got a quiz coming up on Tuesday. That ought to be, and that those are the three major things that are coming up. I have all of the grades currently as up to date as I can possibly make them. So if you're looking at your grades and trying to figure out where you are, this is the best and most up-to-date thing that I have. So things should look about how you'd expect them to look in terms of grades. Today we're going to go over the sort of the second half of the chapter that deals with Lewis structures. Lewis structures are a hugely important concept for us because next week we'll start actually drawing molecules and assigning them shapes, and based on their shapes they're going to have properties. So that continuum of things really kind of starts in quantum, but it sort of like really nucleates, to use a word that's common amongst us. It really nucleates in Lewis structures, and then it kind of carries on into structures, 3D structures at least, and properties of those structures, which we'll get to kind of at the end. So we ought to be good, right? We should finish on the same topic I kind of expect us to finish on. Okay, so with all that said, I'll break for questions in a little bit, but why don't we just sort of dive into the things we have, because there is a fair amount. So go here to resonance. And 5, good. Annotate. I appreciate the patience you guys have for me each week as I do this probably less cogently or less nicely than some of your other instructors do, I'm sure. Okay. Good. All right, so we're going to go into a concept called resonance. And if you were to draw the nitrate anion, NO3 minus, and incidentally, that is how a question would be asked on a quiz or test. Draw the Lewis structure for the nitrate anion. It would be up to you to remember that it's NO3 minus. You know, before you just dive on the internet and see what that is, just realize that this is something you are fully capable of doing. So nitrogen has 5 valence electrons. You can find that out on the periodic table. Oxygen has 6. There are 3 of them. So 5 plus 6 times 3 is 23. And then there's this negative charge, this minus. And that minus means that we've got another electron. So I have this minus equals 1 thing. That's what that means there. So the sum of 5, 18, and 1 is 24. So our structure should have 24 valence electrons. And I have drawn it here. So this is what the first of them would look like. And I can go through the exercise of drawing good and bad ones, but for the most part, this is where we land. So I've got 2 single bonds, 1 double bond. Here I've got an octet around oxygen. Here I've got another octet around oxygen. Here I've got another octet around oxygen and an octet around nitrogen. So 3 groups of 8, that's 24. So all my valence electrons are accounted for. Everyone has an octet. We're happy. But that double bond, I have it drawn up here on top. It doesn't have to be. I chose that oxygen randomly. It could be on the bottom left or it could be on the bottom right. And the fact that it can go between any of those spots is what we will call resonance. That is that double bond can move around. And as you may notice, a pair of lone electrons can also move around so that, you know, every oxygen atom has a little bit of time being this kind of atom or this kind of structure. The best and the rightest way for us to represent these kinds of structures is with brackets and with the charge on the outside. So if you were to say that this is the Lewis structure for nitrate, you're only mostly right. To be completely right, you would need to show that there's a bracket around here and a negative charge on the outside, and that negative charge means that somewhere on this entire molecule, something has a charge of -1. Okay, this entire thing has a charge of -1. That's what the bracket is there for. And to show that there is resonance, that we're not saying it's just this one, or just this one, but it is in fact all 3 of them, we use these double-headed arrows here. Individually, any one of these is called a resonance contributor, okay? And they all contribute to, and this is a static state, so this is kind of what we think they look like if you took like an individual picture, but if you were to sort of take millions of pictures and play them back really, really quickly, you would see that that double bond just kind of fills this entire space. And so there is a single bond between every nitrogen and oxygen. And then there's a partial double bond between every oxygen and nitrogen. And this is what's called the resonance hybrid. And this is the molecule that really exists. However, dashed lines are sort of fuzzy, so we tend not to use them to represent molecules. But this is the real molecule. This is what really exists. And resonance is lone pairs and double bonds that move, but atoms do not move. Atoms are locked in place. So only certain molecules will have resonance structures, and it'll be up to you to recognize where those are. Usually they'll contain double or triple bonds, as well as lone pair electrons that can move around. And it results in something that is delocalized. The electrons here in this bond are what's called delocalized. They sort of spend their time over the entire molecule. So there are two molecules here, ozone, O3, and the other one, CH2Cl2, methylene chloride. And if you were to draw the Lewis structure for this one, there should be 18 valence electrons. And we did this one in class the other day, so I won't go through that. But this one here has two structures that are available to it. When I draw the structure for it, the only way I can really get 18 is for there to be a double bond and a single bond. But the double bond doesn't have to be first, it can be second. And so there's resonance between these two structures. Over here, CH2Cl2, there's no double bond that moves around. So I really don't have resonance. But if I was to draw it as Cl on top and Cl to the right, as opposed to across from each other, those molecules are identical. They're not in resonance with each other. Resonance is the movement of electrons and bonds. This would be the movement of atoms. They are not identical. Okay. Now the coolest graphic of this actually comes out of the organic chemistry textbook. Your textbook uses a couple of dogs. I think this is much better. So on top, what they're saying is there's a unicorn and a dragon, two things that don't exist. And I'm so sorry if I'm breaking any hearts out there. But those are the resonance contributors. Resonance contributors are fictional things. So none of these nitrates really exist. They just represent, okay? But the hybrid is the molecule that really does exist, and it's the mixture of these two. So what they're saying here is that a rhinoceros is the hybrid of a unicorn and a dragon, and a rhinoceros does in fact exist, okay? So remember, unicorns and dragons don't exist, rhinoceri do. And these are resonance contributors, and this is the resonance hybrid. So I always thought that was a cool graphic. Now let's take a look at this molecule, thiocyanide, SCN-. It is one of the ones that you would have learned early in the semester when we were doing nomenclature. And it's got two more resonance structures, including this one. And I just sort of drew them out. Okay, and what we can do is we can move a pair of electrons. We can move this bond over here. And we can do it again. So we arrive at, so this is what was given originally. This is another version of the same thing. This is another version of the same thing. Sulfur brings 6, carbon brings 4, nitrogen brings 5, that's 15, and -1 charge. So the whole thing is -16. Okay. I think we have a microphone on out there. So if you intend for that to be on because you want to ask questions, great. If it's on by accident, maybe just double check. Okay. So these are the 3 resonance structures that we can have with that. And we're going to come back and qualify how good they are later, but we're going to get into a concept called formal charge. So this idea of formal charge, your book has what would be a textbooky kind of description. And it's the charge of an atom in a Lewis structure if all of the bonding electrons were being shared equally, which is not the case. Your book goes into electronegativity before it goes into this. So we know that this is a bit of a fiction, but it's a very helpful fiction that we're going to want to pay attention to. All right. So the way we calculate formal charge, and we will calculate this, but it doesn't require any advanced math. This is really quite straightforward. For any atom, like the nitrogen atom here, or the oxygen atom, we would figure out how many valence electrons it has. So you'd go to your periodic table, and you'd look to see, here's nitrogen right here. Nitrogen has 5 valence electrons, oxygen has 6. Okay, so for nitrogen, there are 5 valence electrons. Now we want to subtract half the bonding electrons. So there are 2, 4, 6, 8 bonding electrons. Half of them belong to nitrogen. So that's why this half is here. So half the bonding electrons, so 5 minus half of 8, which is 4. minus all the non-bonding electrons. That means any lone pairs. Well, there are no lone pairs around nitrogen. There are some around these oxygens, but none around nitrogen. Okay, so the formal charge for nitrogen would be +1. 5 minus half of 8 minus 0 is +1. I always struggled with this half of bonding electrons thing. I felt it was clunky. So if I just count the number of sticks that are here, it's the same number. If one of every electron in each one of these bonds belongs to nitrogen, it's the same as counting the number of bonds that nitrogen has. So 4. So if I was to do this again, I would just say 5 minus 4 minus 0. 5 minus sticks minus dots. And I'd still get to +1. And if I do that for oxygen here, this oxygen, this one on top, there are 6 valence electrons for oxygen. This one here on top with the double bond has 2 bonds and 4 lone electrons. 6 minus 2 minus 4 is 0. So this oxygen here has a formal charge of 0. These two oxygens, they're identical, so I only need to do it once. Still has 6 valence electrons. There's only 1 bond right there, and there are 6 lone electrons around it right there. So 6 minus 1 minus 6 comes out to be -1. Okay? So if I was to draw those in there, this has a formal charge of -1, this has a formal charge of -1, this has a formal charge of +1, and this has a formal charge of 0. One of the things you might notice is that if I added all these up, -1, and +1, it comes out to -1, which is the sum total charge of this molecule, or this ion in this case. So that's one of the things that's handy. Formal charge kind of pretends like there's an individual charge on every single atom in a molecule. And there are some rules that we can use to make this work to our advantage. So here's one rule, and we just sort of exposed it. The sum of all formal charges is going to add up to the total charge of the species. So for nitrate that you saw there, all the formal charges there add up to the charge of nitrate, which is -1. So -1 on 2 of those oxygens, so -1, -2, a +1 on the nitrogen, so we're back down to -1, and the other oxygen is 0. So they always add up that way for every single molecule. And you can see it here. Okay, so I just described it, +1, 0, -1, -1. Add those together, you get -1, which is the charge of nitrate. So we know that we've done this correctly. Second, the best Lewis structures have the smallest value of formal charge. So that is, if you're going to have a value for the formal charge that is not 0, okay, you can't have a smallest value of 0. 0 is its smallest value. You want the value to be as close to 0 as possible. That is, -1 is much better than -2. +1 is much better than +2. So that means that there's not a lot of charge built up on any one atom in a bond. Okay, so if you drew a Lewis structure and there is a +2 formal charge on one of the atoms, we're going to want to take a second look at that because that's probably not a good representation of that molecule. Third rule is that the best Lewis structures have the smallest number of non-zero charges, formal charges. So if you're drawing a molecule and every single atom in that molecule has a non-zero formal charge, +1, -1, whatever, then chances are you can do a better job of representing that molecule. We want the smallest number of non-zero formal charges. And the reason we want that is because molecules don't really have much separation of charge, or shouldn't. The best Lewis structures have negative formal charges and more electronegative atoms. We have not yet covered electronegative atoms. You probably remember it from your previous class. Oxygen's more electronegative than nitrogen. So if you're going to have a formal charge on one of these two atoms, putting a negative formal charge on oxygen is better than having a negative formal charge on nitrogen. This is more. Who's got a cat? Spooked my dog. Okay. So, and again, maybe just double check those microphones unless there's a question you want to ask. Best to have dog owner. So going back to this thiocyanide, we should be able to get the formal charge for every single one of these atoms in every single one of these structures. There's only 3. It's pretty easy to do. So let's see how we would do it here with this first one. Sulfur brings 6 valence electrons. Cameron, I think your microphone's on.
Got.
Hold on a second, guys. I'm going to see if I can mute him. Muted. Okay. 6 minus 2 minus 4. So I've got 6 valence electrons. There are 2 bonds to sulfur and 4 valence electrons. Okay, so that has a formal charge of 0. Carbon has 4 valence electrons. There are 4 bonds to it and no lone electrons, so it has a formal charge of 0. Nitrogen has 5 valence electrons. There are 2 bonds to it and 4 lone electrons around it, so it has a formal charge of -1. This has an overall formal charge of -1, so we know they add up correctly. So if you would please try that. I'll give you about half a minute to try that for these 2 structures here. Do the exact same exercise for these 2 structures. We should be able to see that one of those 2 structures is better than the other. So give that a shot. I'll give you about half a minute. Okay, so if we were to look at it, sulfur here has 6 valence electrons. There are 3 bonds to it and a lone pair, so it gets a +1 formal charge. Carbon is still 0. Nitrogen here has a charge of -2. Sulfur here has the formal charge, 6 valence electrons, 6 electrons around it, 1 bond to it, so it has a -1 formal charge. Normally these 2 would be reversed. It's just laziness on my part. 0 and 0 for the others. So in terms of overall quality of formal charges, this one over here is good. This one over here is good. This one here in the middle is not so good. Now between these 2, we need to know what's more electronegative, nitrogen or sulfur. It turns out nitrogen is more electronegative. So this is the best of the Lewis structures. This one is not a very good Lewis structure, even though it follows all the rules. And this one over here is an okay Lewis structure. Okay, so it allows us to qualify if Lewis structures are good or not. So let's look at the sulfite ion, SO3 2-. It's got a -2 charge. Again, on a quiz or a test, I would say what is the form, what is the sulfite anion? So you'd have to actually know that. So sulfur brings 6 valence electrons, oxygen brings 6, and there are 3. And the whole thing has a charge of -2, so we add an additional 2 electrons. So that's 26 valence electrons there. So if I was to draw the Lewis structure for that, it's pretty easy. There are 3 groups of 8, so octet, 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 and then this sulfur here has 2, 4, 6 electrons in bonds and a lone pair. So that is a Lewis structure that is quite good. At least it follows all the rules in the octet rule that I'm familiar with. If we do the formal charges, however, we get a different story. Each oxygen there has a -1 formal charge. Okay, 6 minus 6 minus 1. The sulfur there has a +1 formal charge. 6 minus 3 minus 2. So that means we should probably do better. The best Lewis structures have the smallest number of non-zero formal charges. We should be able to at least eliminate a +1 and a -1. So how do we do that? You may be shocked because what you're looking at is a violated octet rule. Take a second to compose yourselves. I assure you this is fine. I have not been hacked. The sulfur atom here has 2, 4, 6, 8, 10 valence electrons around itself. Is this okay? Well, I wrote it down in ink, so it must be. If we do the formal charges for this oxygen now has a 0 formal charge, 2 bonds, 4 lone electrons. This has a 0 formal charge, 4 bonds, 2 electrons, and these both have -1s. They add up to -2. So this works out as a better structure, but it still doesn't explain why I am seemingly okay with violating the octet rule here. And the reason for that is this. If I was to look at the electron configuration for sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p4, and that is its electron configuration. However, there is room here for 3 Ds. That is, in the third energy level, there are d orbitals available, even if there's nothing in them. So if you're looking at the periodic table here, right, and you've got the third period going across, this is where n equals 3. Here it's where n equals 4, n equals 5, and so on. In any place where n is larger than 2, you can go above the octet rule into what's called an expanded octet. So the octet rule really only applies to second period elements. As a rule, most other elements do actually try to fill out their octets, have 8 electrons around them so that they can be, full and happy, and that's great. However, there is space beyond those octets in the D-shaped orbitals and beyond. So those atoms can get more than 8 electrons around themselves. Okay. So I did another movie. I don't think I uploaded it to your site yet, but I will, where we kind of go through this exercise. Xenon tetroxide has 8 plus 24, 32 valence electrons, and you'll find out if you do a Lewis structure for this and look at formal charges that this is the best way to do it. So in the chat, try this out. Okay, I want to see what, let me get over to the chat so I can see. What is the answer to this question in the chat? What is the formal charge of, what is the formal charge of the sulfur atom in the best Lewis structure of the sulfate anion? Okay, so the formal charge of sulfur in the best Lewis structure of the sulfate anion. So please take a minute to try that out and see if in the chat you can give me an answer. About a half a minute or so to try it. And for those of you that need help, sulfate is SO4. It's got a 2- charge. Sulfate anion. So in the chat, please, write what the formal charge of the sulfur atom would be when you draw the best possible Lewis structure of the sulfate anion. Erica has come back with a charge of 0. She is absolutely correct. Now, I'm going to load up my video here for a quick second, because that's where I've got a good drawing of this. I added this last minute. So Erica shows a charge of 0. As soon as I get this video loaded, I will share that portion of it with you so you can see. So I'm going to stop my share here. Hope you're all doing well. Oops. Come on, YouTube. This shouldn't take anywhere near this long. In this video, we're going to talk. All right, so let me mute the video and show you this. Oops. All right, so I'm going to go back to sharing my screen here. So thank you for your patience. Okay, so I'm going to share this screen here. And put up this. This is the structure that you're looking for right here. This one. Okay. When you do this, if you follow the octet rule, this is the structure that you end up seeing. And following the octet rule gets us something that has way too many formal charges that are not zero. So this one does a much better job, and it violates the octet rule. This is in a new video that I've posted, and I'll post it to my courses in just in a few minutes, as soon as class is over. But that's something that you definitely want to pay attention to. Okay. All right, so I'll stop sharing that so I can start sharing something else. Okay. Now, this is just a touch on electronegativity. So electronegativity is, it's a quality of an atom in a bond. Okay, so atoms that are in bonds are the only atoms that have electronegativity. Otherwise, it's something that is sort of like just talked about. So it's the tendency to attract electrons while atoms are in a bond. So if I have the HF molecule, hydrogen fluoride, this is what it is. Okay, draw the Lewis structure for it. That's the totally right Lewis structure. What I expect is that there is this bond right here is a pair of electrons that are being shared between hydrogen and fluorine. Fluorine's got 6 other electrons around itself, so it's got an octet, it's happy. Hydrogen's got a duet, it's happy. And that is my expectation. In reality, however, these electrons are being selfishly shared. So fluorine is sharing them, but not really giving them up all that often to hydrogen. So these electrons spend a lot more time around fluorine. And as a result, a partial negative charge builds up around here. So this little squiggly d is my wrap name. This lowercase delta has a partial negative charge around fluorine. And here I've got a squiggly d positive, meaning because this doesn't have electrons around it very often, it gets a partial positive charge. The overall charge of this is 0. But this part of the molecule is kind of negative, and this part of the molecule is kind of positive. There's a consequence to that. And that is that if this molecule is out here floating and another molecule comes by, this partially negative end is going to be attracted to this partially positive end on the other molecule. So there's a force of attraction between the two. And we see that this molecule would be kind of stick to itself, okay? And water does the exact same thing. Water is a rather sticky molecule. It beads up, it sticks to itself. So on the periodic table, fluorine is the most electronegative element, and as we get closer and closer to it, electronegativity increases. So from left to right and from bottom to top of the periodic table. There are tables that you can look up in our book that will give you exact numbers on electronegativity. There's a number you can throw at it. I think it's measured in dynes, but those aren't things that we ever really deal with. The trend is, as you get closer to fluorine, this becomes a lot more electronegative. Okay, so I'll stop my share there. Do any of you have any questions over any of the content that was covered there? Anything you want to ask? Okay, so there's one more thing I want to cover with this. It's a direct application of that. And that is this. So give me a second, I'll get to the right spot where I can share this. Coffee's bitter. My coffee is bitter, I should say. Okay, so go back here to annotate. We're going to talk a little bit about cocaine. Crack or cocaine, know your nose candy. And I'm going to want the chat open for this, but I'll get to that in a minute. Okay, I'll move this over here to the side. All right, so this is crack. This is kind of, this chat thing here is kind of part of the molecule. I'll minimize it. So this is the molecule now where any 2 lines meet, there's a carbon atom. This hieroglyph is something we use a lot in organic chemistry. 2 things that are commonly not shown in stuff like this are lone pair electrons and hydrogen atoms. So they're here, trust me. But this represents the molecule that we now know and love as crack. So look at this nitrogen atom here. This nitrogen atom actually has an octet. There are 1, 2, 3 bonds associated with it, and there's a lone pair that's not shown. So this is what's called a tertiary amine. And the formal charge on this nitrogen is 0. This molecule is also what's called nonpolar. We'll get to polar molecules next week. And because it's nonpolar, it's very fat soluble. Because it's fat soluble, it forms like these little waxy rocks, which must be smoked if you're to enjoy this. Don't do that. Let me show you cocaine now. You ready? There's a big difference. That's cocaine. That's crack. That's cocaine. That's crack. Here, let's take a second look at cocaine. Now there is a single hydrogen atom that's been attached to this nitrogen atom. Now this is a nitrogen atom with 4 things attached to it. It's got an octet, but its formal charge becomes +1. 5 minus 4 is 1. So there's a +1 formal charge here on this nitrogen atom. That makes it a quaternary amine, and it's charged. Because it's charged, it dissolves in water really easily. So it becomes water soluble. That means that you can get it into your body via injection. And the white powder that you may have seen it shown as is cocaine hydrochloride. That is, that there's usually a Cl attached to it here. And you want to ask for it by name. Okay, just sounds smart. So again, crack and then cocaine. So this leads me to a question you guys can answer in the chat if you like. What is the cost of a crack rock? Is it $1 to $5, $5 to $10, $10 to $100, $100 to $500, over $500, or you don't know? You can answer in the chat if you like. If you don't know, and that would be the right answer for this, I don't know. Just keep that dollar amount in mind. What is the cost of 1 gram of cocaine? $1 to $5, 5 to 10, 10 to 100, 100 to 50, over 500, or I don't know. You can make a guess, but hopefully your guess is I don't know, because you should not know this unless you study it. And actually the economics of the drug trade are fascinating. But if we move on here, it is an expensive atom. So crack costs about $5 to $15 per rock. Okay, and that's how they can end up being bought. Cocaine, on the other hand, and one of the things that happens with this is that it has always been known to correlate with rates that are charged for prostitution. So as crack prices go up, so rates for prostitution, and so on, and down, and so on. Cocaine, however, goes for about $150 per gram. And every now and again, I have to update this slide. It's an expensive drug. Considering that your body does not really know the difference between the two, it's an expensive drug. As soon as your body sees this drug, the pH in your body takes over and one will become the other, okay? So if your body has a certain pH, that nitrogen atom will absorb that hydrogen atom, and your body will just quickly work with this stuff, whether it goes into your body as crack or as cocaine. They're identical as soon as your body sees them. Interestingly, the sentencing for crack was 100 times more severe than cocaine. That is, if you had 100 grams of cocaine or 1 gram of crack, they were treated the same in terms of punishment. Okay, so basically, to have 100 grams of this stuff, you'd have to have 100 times $150. So that'd be a lot of money, $15,000. If you had 1 gram of this, you'd only have to spend $5 or $15. And this negatively affects people who can afford this. So the social justice surrounding this is really quite bad. So there was something for a long time called mandatory minimum sentencing. And the Fair Sentencing Act changed that to 18 times more severe. So roughly went down by a little more than 80%. Now, the only thing that's actually fair here is equal punishments for the same thing. As far as your body is concerned, these molecules are identical. The only thing that's different about them is how quickly you can get them into your system. And because crack ends up being smoked and inhaled, that is one of the fastest ways things can get into your system. So the Fair Sentencing Act changed this. So now it's only 18 times more severe. So 1/18 of this amount is the same as having any of this amount. And mandatory minimum sentencing, if you ever want to take a look at that, that is the sort of the level of punishment that is expected for various levels of crimes. The cool thing about this, I am very interested in drugs and how they work and economics of drugs. It's a really, to me, it's a really cool thing to think about, is that it does literally come down to one hydrogen atom and the formal charge around that one nitrogen right there. Everything else is just a molecule and other chemistry, but whether or not you are a person buying this or a person buying that, it comes down to what is surrounding a single nitrogen atom and the concept of formal charge. Okay, I will stop the share there. That is probably your single most amount of information on crack or cocaine that you'll get all day today. I hope. I'm pretty sure those are not as fashionable as they were when I was growing up. Okay, so are there any questions, concerns, comments, anything for the good of the order? We're down to less than a minute on this, and so we get cut off rather unceremoniously. So just remember, extra credit is due on Saturday, homework due on Sunday, quiz on Tuesday. You'll get emails and updates from me about what sort of things to pay attention to. Okay, so if I don't hear anything from you, have a good evening. I'll see you next time. Bye, guys. Miss you all. Really wish I could see y'all. How long will this video be up? Oh, you mean like this conference? Not much longer. But email me if you want to talk. Bye, Erica. Email me if you want to talk. I can open up a new one, okay? Because I started this with more than 2 people, it'll just cut me off.